Good afternoon, everyone. Thank you for attending this semester's Brown Bag Lunch Seminar. This is our first seminar this semester. Uh, Unfortunately, and we have we have to conduct a virtual seminar this semester. So I think, but still, I think it's well attended. We have about 24 attendance, even without a pizza. Uh, Today is our great pleasure to have Ted from ASEL to present the candidate engine for a supersonic business jet. And before I start to introduce Ted, so please be reminded and please keep yourself muted and during the presentation. And after Ted's presentation, you're welcome to turn your microphone on and ask him questions if you have any. Okay, so now let me introduce Ted. Ted is a fifth-year undergraduate aerospace engineering student. He currently works as an undergraduate researcher at the Aerospace System Design Laboratory, ASTL, everyone knows, in the propulsion and energy group. His interests lie in gas turbine engine performance modeling and component design. He has interned at Honeywell Aerospace in 2018 and GE Aviation in 2019 and 20. Okay, so Ted, now I'm handing the microphone to you.
Thank you, Dr. Sun. So today I'm going to talk to you guys about the YJ2030, which is a candidate engine for a supersonic business jet. And this project was part of the AIAA Undergraduate Engine Design Competition. To give you some background on the project itself, each year AIAA organizes an annual team engine design competition. And it's open to all undergraduates across the world. And they typically provide a request for a proposal, and teams will deliver a 100-page report. And then if they're in the top 3 reports, they'll be selected to round 2, where they'll give a 20-minute presentation. This is my second time participating in the competition, and we actually won this year. We won the 2020 competition, so you can find a report on my website or on the AIAA website, along with more information about the competitions. So I'll start off with an executive summary of our engine. So the YJ2030 is a candidate engine to be installed on the proposed supersonic business jet. The design I'm going to show you today contains information regarding the requirements, cycle, components, flow path, and weight of the engine. As you can see in the picture, our engine is an afterburning mixed flow turbofan that has Mach 3.0 capability, is 4.6% lighter than a baseline engine provided in the RFP, meets stage 5 noise constraints, which are the strictest noise constraints out on the market right now, and has a range of 5,300 nautical miles at Mach 0.98, which is the subsonic cruise Mach number provided in the RFP. Now to actually define the problem. So the RFP is seeking to re-engine their supersonic business jet. It has a cruise Mach number of 2.1 at 40,000 feet, a sea level static thrust of 22,000 pounds thrust. Proposed engines must fit within the existing nacelle, so they do not have to change the aircraft too much. They're predicting the engine will go into service in 2030. And while no explicit requirements are given, they want us to consider noise and emissions of the engine. We're going to be delivering an optimized engine cycle, detailed component design information, and a flow path and weight estimate. So any good design really begins by setting a good design process. So we start off with defining the requirements. So these come from the request for proposal from AIAA, and also requirements set by the regulatory agencies like FAA and ICAO. We also create a baseline mission in this step and model the baseline engine so that we can get a good comparison between different engine models and architectures. The next step is developing the architecture of the engine, so setting whether the engine is a mixed flow turbofan or an afterburner, high bypass turbofan, things like that. We're also going to be optimizing the engine to maximize range and determining performance characteristics like mission fuel burn, TSFC, things like that. The next step is really just determining the component architecture, geometry, and materials and manufacturing of each subcomponent, whether that be a fan, a turbine, a combustor, etc. And we're also going to be analyzing the off-design behavior. And then in this step, we're going to be analyzing maps. So as we change the throttle and as we change altitude and Mach number, component performance changes. We want to study that and potentially flow any of that information up to our cycle. And then lastly, we're going to be analyzing the system as a whole and determining whether we meet the requirements that we set in step one. And then as the point in red states, it's not really a linear process. Multiple iterations between steps, flowing information back and forth is really important, and you'll have to make some compromise between the overall design process to best meet our customer requirements. And now, speaking of customer requirements, we define these in starting with the most important, going down to the least important. The most important thing that we deliver to customer is just thrust to make sure that the engine can allow the aircraft to fly across its flight envelope from Mach 0 to Mach 3.0. So we determined the thrust required by recreating a figure that was given to us in the RFP. And then we also create a baseline mission in the step. So at this point, we say the engine needs to take us from New York to London, and we apply this mission to every single engine we'll study. The next most important requirement is that the engine must fit within the nacelle envelope, and we prefer lighter engines. So as I kind of mentioned earlier, the airframer really doesn't want to change their engine or their nacelle too much. So if we can provide an engine that pretty much just slides into its existing space, it'll be great. And then lighter engines just mean that we can have an increased range. Then we have emissions. So emissions are really typically set by a regulatory agency called ICAO, and they determine how much emissions you're allowed to emit based on your overall pressure ratio of your engine at a sea level static, and then they'll just give it to you as a function of your thrust, really. And then they also define a cruise emissions goal that's given in literature. And lastly, for noise is really difficult to measure. Typically, if you would need some high fidelity analysis, and we just don't have access to those tools, so we can use the exit jet velocity as a surrogate. And so literature suggests that we need to keep 1,100 feet per second jet velocity to meet the stage 5 noise constraints. So now we'll jump into the cycle design process. It begins by selecting a single architecture for our engine. So unfortunately, we can't test multiple architectures just due to manpower and time constraints. So we have to determine single architecture and then determine whether we need an afterburner in this stage. After we've determined that, then we'll develop our model. We use a modeling software called MPSS, and we are setting our component efficiency, losses, and offtakes based on what literature suggests is best for similar engines. The next step is just doing trade studies on our model. So we're optimizing our range, and we're varying things like bypass ratio, fan pressure ratio, overall pressure ratio, and T4 within requirements that are set by literature so we can best optimize range. And then finally, we use a final mission analysis to determine mission fuel burn. And we also do a performance management or power management study, which pretty much just says, like, does our engine meet the thrust that we need to meet across the flight envelope? And if not, we need to change some things on our off-design maps. So I'd like to share some of the cycle design and trade study results. So first of all, our engine is a mixed flow turbofan built in NPSS. And NPSS is really nice. It's a lot more robust than other programs that you may make in MATLAB or other programs that are out there because it allows us to modify elements, allows us to do very specific things that we want to do, lots of user customizability. And so we choose to minimize mission fuel burn plus engine weight because that correlates best to maximizing range. And so we could have just minimized mission fuel burn. However, we could end up with an engine that's really heavy, and it doesn't make sense anymore to have that really optimized engine if we're going to have a heavy engine that offsets those savings. So in those two figures, you can primarily see that we're limited by our fan diameter constraint and our T3 constraint to improve our range. And so T3 is typically the exit temperature of the compressor, and that's limited by materials. However, the fan diameter is limited by our airframer. So if the airframer is willing to increase their fan diameter on their nacelle, they can significantly improve the range of their aircraft. So now just to go into cycle outputs. So as was mentioned earlier, our engine is the afterburning mixed flow turbofan. It has 2 spools with a 3-stage fan, 6-stage high pressure compressor, 2-stage high pressure turbine, and 2-stage low pressure turbine. And we only really need the afterburner to reach speeds greater than Mach 2.1. So if for some reason the business jet wants to cruise faster than its cruise speed, we can reach that up to Mach 3. Our design point as specified in the RFP is Mach 2.1, 40,000 feet. I won't go into the specifics of our cycle, but you can see that our engine is a low bypass, really high T4, low OPER engine at cruise, which is very different than what you would see a commercial high bypass fan at a cruise to be. And so the key point here, so at our pinch point of Mach 1.15, we see a lot of thrust. So that's when we have to break through the sound barrier. And that's typically when we need the most relative thrust. So that means we'll have the fastest fan speed. And so we actually have a higher fan pressure ratio at Mach 1.15 than we do at Mach 2.1. So 33% higher. You can see how much the fan pressure ratio changes as we move altitude and Mach number and throttle. Okay, so now that our cycle design is done, we begin the component design process. And again, we begin with selecting a single architecture due to time. And this involves looking at literature and just qualitatively determining which one best meets our requirements, typically done in like a Pew matrix. The next step is just developing the equations into models. So we would develop a model in MATLAB, and we'd create a parametric model so we can vary a ton of different variables, so we can test a bunch of different models and components to see which one best fits our requirements. We do this in the design step, and we're making engineering decisions based on for our inputs, and we're checking, does this component make sense? Is it violating any major issues? Things like that. And then at the same time, we're also looking at the off-design performance. So as I mentioned, we're looking at the maps of the components. So just like the fan pressure ratio changes as we move altitude and throttle, a lot of the other components change. So we need to make those considerations. We need to look at if we're violating any rules, and we can flow that information up to our cycle and make any changes as needed. And finally, we're looking at the materials and manufacturing for each component. So it's great that we've designed this component, but if it can't be manufactured, if it doesn't have a material that can withstand the stresses, it doesn't make any sense to implement. So we need to look at the technology readiness of each material, look at the risk, look if it can even be manufactured. And this is really considered throughout the process, but it's fully finalized in this last step. So now we'll talk about the inlet. So we'll just go from component by component across the engine. So the inlet is a 2D 4-shock inlet, and we chose this because it offers the best combination of performance, weight, length, and reliability out of the inlets we looked at. We optimized the inlet for its best cruise pressure recovery based on oblique shock relations that you may have learned in thermodynamics or fluid dynamics. We actually shortened the throat length and the subsonic diffuser angle because one of our customer requirements was that we had to fit within the envelope, so it was important to make sure we do that. And we also considered off-design behavior of our inlet. So the inlet creates a lot of drags. It has off-takes, so we'll have a bleed off the inlet, we'll bleed off the boundary layer, and that needs to be mapped and modeled into our engine. So we use these NASA tables that predicts how much drag we'll see from each off-take from the inlet. And now I'll talk about the fan and the compressor. So just to go over our approach, we created a mean-line design MATLAB code from axial compressors. So this is something you might do in like your 4803 class on like advanced gas turbines. So we kind of modified this code, and we had cycle inputs and design parameters that we input into our compressor, and then we looked at different designs. We looked at their flow path, we looked at velocity triangles, and we looked at the 2D blade analysis to see if our design was actually viable. And if it wasn't, we had to do another iteration. And so the picture on the left you can see is the fan. And so our fan really prioritizes beating that fan diameter constraint set by the customer. And so we had to go with the 3-stage design, some pretty high and pretty aggressive design choices. So we had to discount some of our efficiency, our fan efficiency on design. In terms of the high pressure compressor, since our fan was super risky, we wanted to take a low risk approach to this, and we wanted to focus on making sure it was manufacturable. So really we're looking at the stresses of our compressor. We're looking at the blade heights to make sure they're manufacturable. And so it ended up being the design values were not too overly advanced, so we didn't really take a efficiency hit on the compressor. Now to move on to the combustor. Our combustor architecture is really just chosen, again, in a few matrix, evaluating things on stability, efficiency, emissions, pressure loss, and lifetime. And so there are three general types of compressors combustors that people will look at right now. Lean premixed, which is like a GE TAPS combustor, rich quench lean, which is like a Pratt Whitney type combustor, and a dual annular combustors. And those are kind of on your older engines. And so lean premixed perform best across all categories, and thus we try to design it. And the issue with this is lean premixed combustors don't have a lot of information on the internet about how to design them, mainly because it's proprietary information. It's a pretty new design by GE. So what we had to do is just adapt a design process written from textbooks and apply it to this type of combustor, this type of architecture. And so we had to, look at a lot of literature, and we had to reverse engineer some of the engineering drawings that are out there on a lean premixed combustor, which is the TAPS combustor, and just reverse engineer that and figure out ways to apply the design process. And again, customer length is a big requirement. So we made sure that we shortened our combustor length while still meeting some of the requirements that we had to, like residence time. Now to go over the turbines. Design approach is very similar to the compressors. Some of the inputs are different, some of the equations are different, but generally how we're doing this is very similar. The HPT prioritizes long lifetime. So if you think about what a commercial turbofan engine is, really big on like a Boeing 777, they only operate at high T4s at takeoff. And then when they're cruising, the T4 is relatively low. However, for a supersonic engine, it's the exact opposite. You have low T4 at takeoff, and you have a really high T4 at cruise. So you're staying at high T4 throughout cruise, which is pretty bad for your turbine unless you prioritize long lifetime. So we chose a two-stage design. It limits the heat load on the second stage because the first stage is extracting most of the work, and thus just the first stage needs to be cooled. The second stage does not. And then that last little bullet says that our hub reaction is above zero. This is just a design rule to make sure that the angles we chose on our blades are viable. For the LPT, we just prioritize as low weight, so as few stages as possible. And this ended up being a two-stage design. And then we chose zero exit swirl, so that's just a design choice to make sure that we don't have any exhaust losses. Now, speaking of the exhaust, we have three components that are part of our exhaust system before the nozzle. They're the mixer, the afterburner, and the mixer ejector. And so we had them share a common duct because it allows us to shorten the length of the engine. And so really the mixer ejector only operates at takeoff because it's a noise suppression system. And the afterburner, like I mentioned, is only operable at Mach 2.1. So it's really these ducts don't need to be used at the same time, or these components aren't used at the same time, so we can do this. And the architecture and design of these components is really hard to do because it requires a lot of high fidelity analysis that we really don't have access to. We don't have the time to run a lot of CFD simulations. So what we can do is we can study previous concepts. So up here is a GE Affinity mixer. This is on their newest supersonic engine. And we try and apply that to fit our engine using methods in literature and information from literature. And then the last bullet. So the mixer ejector, like I mentioned, is a noise suppression system. It draws in ambient air, mixes with the hot exhaust, slows it down a little bit, and we're allowed to meet our jet velocity requirement, exit jet velocity requirement. And so maybe some corporate airfields do not require stage 5 noise requirements. So thus we can remove this mixer ejector, make our engine simpler, make it lighter, and just overall improve range of our aircraft. Oh. Okay, let me try this again. Okay, so now to our nozzle. We chose a fully variable converging diverging nozzle due to its performance benefits. The CD nozzle performs best at high nozzle pressure ratios, which is typically what supersonic aircraft will operate at. And so we had a variable exit area and also a variable throat area. And the throat area is needed to be variable because when we were operating the afterburner, we could severely mess up some of the components upstream of the afterburner, especially in the fan, if we're not opening up the area and decreasing the back pressure. And so some of the, again, like the nozzle or like the inlet, there are a lot of drags that are associated when the flaps are opening and closing. So we need to model those drags so we're not over predicting our thrust. And we do that just with NASA curves. And lastly, we can optimize our nozzle area so that we can achieve the best thrust specific fuel consumption while offering still a good stall margin on our fan. Now to go over quickly on the geometry and material analysis. Typically you'll see on like high bypass fans, you'll see carbon composite fan blades. However, they don't work well at high temperatures at Mach 2.1. So we had to go with a different composite called polyimide. And now we'll move into the compressor. The first three stages are typically standard. You know, titanium alloys are used throughout the industry for compressor blisks. But the last three stages, because we're operating at a high temperature at Mach 2.1, Mach 3, we need titanium aluminide alloys. So that's just a different material. It's lighter than what we could have used like nickel. So it's pretty advantageous. The exhaust section, combustor, turbines are all made of ceramic matrix composites. These are top of the line, newest material that are typically used in commercial turbofans, and they're quite expensive. However, the rich people can afford it. They're already paying for a business jet that's supersonic. They can afford a little bit more expensive materials on their engine. And so we'll put all this information into a code. It'll spit out a weight in this little pretty picture that I've showed here. And it comes out, the weight comes out to be lighter than the baseline engine by 150 pounds. Its fan diameter is the same, which is good. Nice slip fit. And then the final nacelle length is 37 feet. However, that's including the divergent part of the flaps of the nozzle, and typically that's not like included in the nacelle length. The flaps are sticking out. So if we cut that out, we're only 8 inches, 34.7 feet greater than the baseline, so 0.7 feet. So okay, this last slide, like why should customers buy our engine compared to others? So we meet the most important requirements while offering a long range at Mach 0.98. And so our engine produces the amount of thrust to get from 0 to Mach 3 because we included an afterburner in our architecture, because we decided to oversize our fan for that Mach 1.15 point, like I was talking about earlier. Our engine fits within the desired envelope, so we can just take out the old engine, put in our new engine with no issues, and our engine meets the cruise emissions and takeoff goals that we set earlier in the presentation. And if we do a quick risk analysis, the fan design presents the most risk to the program due to its high pressure ratio and its high loading values. However, we can just mitigate this risk by either adding another fan stage or decreasing the fan pressure ratio of our engine. So I'd really quickly like to acknowledge Dr. Jerry Seitzman and Mr. Russ Denny. Those are our advisors on this project. And then this proposal wouldn't have been possible without the education that I was given to at Georgia Tech. And lastly, I'd like to thank my teammates, Oscar Klempe, Steve Zakharov, and Soon Hit-on. They definitely helped make this presentation possible, and it would have been successful, and we would have been first place without them. So thanks for listening. Now I can take any questions.
Okay, thank you very much, Ted. Are there any questions from the audience? You can turn your microphone on and start to ask.
Yeah, I have several questions.
Okay, go ahead.
I guess I'll just go in order. Where did you get your T3 limit from? What kind of materials were you assuming for the compressor, and does the engine cycle actually end up running to the T3 limit?
Yeah, good question. So we hit the T3 limit just almost at Mach 2.1. And so we looked at this limit based on what the titanium aluminide materials have typically gone to. titanium aluminide hasn't been implemented in compressors yet. It's typically just been reserved for turbines. So we said we'll make the technology assumption that we can jump to in 2030 to producing titanium aluminide compressor blisks. And so we almost hit it at Mach 2.1, but when we go to Mach 3, the way we limit our engine, the way our power management is set up is we have a T3 limit on it, if that answers your question.
Yeah, no, it does. So from Mach 2.1, are you sitting on the T3 limit?
Yeah, we're sitting on the T3 limit, and we're pretty much sitting on our T4 limit as well.
Oh, you're managing to like maintain both of those?
Yeah.
Oh, interesting. I was also wondering the kind of similar assumption for the turbines, what your like allowable metal temperature you were using for the turbine and how you figured out the required cooling flows for that.
Yeah, good question. So right now, based on just available literature, we've kind of seen that turbines can operate at a blade temperature of like 2800. And so what we
What
looked
units
at,
are those?
a Rankine.
Okay.
Yeah, sorry. So 2800 Rankine. And so what we can do is we can apply two things. First, we can apply like a thermal barrier coating. And we can look at how that, just from based on literature, so Mattingly or different textbooks can show what the improvement of thermal barrier coatings can do. And also, if we look at the trends of how T4 has changed or blade temperature has changed over the past few years, it's gone about 100 Rankine each decade. So based on that, we ended up coming to 3100 blade temperature or metal temperature. And then after that, we used NASA Cool It to determine the cooling flows based off of that. Did
Okay.
I answer your question?
Yeah, yeah. When you used Cool It, were you implementing the algorithm they have in there for penalizing turbine efficiency for cooling?
No, I didn't know how to use it, to be upfront.
Okay, no, that's fair. I was just curious. If no one else has any questions, I can keep going.
Okay, thank you. Other questions? Okay,
This is Carl.
Cal?
Yeah, so this is Carl. So you mentioned earlier you had to shorten your inlet design to meet customer requirements. How did this affect your kind of downstream component design processes?
Sure. So if I can go back to my inlet, so really the two things that let me get my little pen out here. The two things that we shortened were the throat length and the subsonic diffuser angle. So those are both on the higher end of what's recommended. So we actually took a small pressure loss off of that's applied to the inlet recovery. And so besides that hasn't really affected too much of our downstream component design. But I would say like just keeping that customer requirement of minimizing length played a lot into our combustor design and also the afterburner design, the duct length of this had to be all combined. So it wasn't as long as we would have wanted. So we took some efficiency hits in the other components as well. Did that answer your question?
Yep, all good.
I'd like to ask something about the inlet as well. I noticed your weight flow path didn't include the 2D inlet drawing, but does your weight, the value for your engine weight, does that include measuring the inlet?
No, it doesn't. So in the RFP, they didn't include the 2D inlet weight. So to compare apples to apples, we really just included, I think the weight they quoted was tailpipe less. So everything in the engine besides the tailpipe in its weight.
Okay, so from fan face to mixer, basically.
Pretty much, yeah. I think we
Okay.
include the afterburner, though, in our weight estimate.
Okay. And maybe I'll ask you this offline. I'm kind of curious which of the PIPSI maps you use to model your off-design inlet performance.
Yeah, I'll put my email in the chat, or for if anyone has like additional questions, but yeah.
What was your fan pressure ratio again?
So at Mach 2.1, our fan pressure ratio was 3.33, but the design pressure ratio of the fan was actually 4.4. So to give some background to maybe some people who aren't completely familiar with how supersonic cycles work, you typically have this point where you're at maximum fan speed, maximum corrected fan speed, and that's going to be your design point for your fan. And so we're not actually at our maximum corrected speed at Mach 2.1. We hit that at transonic pinch point. So that's where we're designing our fan to.
Okay.
Are there other questions?
I got one more actually. I'm wondering whether did you look at whether your A9 ever exceeded like the rest of the nacelle dimensions, such that the nozzle diverging section was kind of like sticking out from the nacelle?
That was something we considered, but just due to time constraints, that wasn't something that we necessarily looked at too much. I think it came out to be a little bit sticking out too much, so we didn't have time to go back and actually address that. Just we had different priorities and couldn't get to that.
Understood. All right. Thank you.
Any other questions? Okay, so seems like we have no further questions from the audience. And thank you very much, Ted, for today's wonderful talk.
Yeah, thank you, Dr.
Thank you, everyone, for attending today's lunch seminar. Okay, have a wonderful week.
Thank you. Thanks for coming, guys. Bye.